recording? Got it. Yes, sure. No problem. Okay. All right. So thank you again for inviting me to be here. All right. So I'll kind of move on, but I guess this talk doesn't really depend on anything I said last time around. So if you weren't here or went to sleep during last talk, it's still okay. Okay, but right. So what I said that the plan was that to talk about topological and combinatorial theory for topological combinatorial dynamics for two-dimensional homeo and diffeomorphisms, and then to try to, the second part was to try to geometrize this and make these topological combinatorial models into more geometric objects. And this was in analogy to what happens to, so the model behind that we're trying to sort of imitate or emulate is the one-dimensional paradigm. So there's this one-dimensional sort of theory, kneading theory that André also mentioned earlier today, but I'm discussing a different aspect of kneading theory. But so let me just recall what I think I didn't quite, well, maybe I said a bit of this, but I'll say it again. So we start with a multimodal map, that is a map that has finitely many ups and downs, finitely many monotonicity intervals, which we also call laps. Right? And then we define the lap number to be the number of such monotonicity intervals of the function f. But then we can also count, we can iterate the function and count how many laps it has after I've iterated the function n times. So that's L of Fn. And then you do something that is normal in the story. That's, you let n grow, you take the nth root, and then you pass to the limit. It's not hard to show that this limit actually does exist. And that's called the growth, not a growth or growth rate or growth number of the map F. Okay? And then there's this theorem of Milnor-Thurston that says that if the growth number is bigger than 1, then there's a semi-conjugacy of F to a geometric model. Right? So right, the point again is to emphasize that this map here, the multimodal map, really has very little information to it. We're not using very much, well, we're not using at all the geometric or the Euclidean structure on the interval. All we were talking about here is really, there could be an arc without any further information beyond the topology of the arc. And then from this number here, there's some work to be done, and then you realize this what started life as a topological arc as a geometric interval with a measure or Lebesgue measure, and which becomes, well, a measure which turns it into a metric space, and then the semi-conjugacy turns your topological map into a map which is piecewise linear. But not only that, it's piecewise linear and the slope is always the same. It's always this growth number here, well, with positive plus or minus sign, depending on whether you're going up or down. Okay? And that's the piecewise linear constant absolute slope model for the dynamics F, little f. Okay, and that's what we're trying to emulate in dimension 2. Okay. Now the question is, what are the correct analogs in dimension 2 of such such piecewise linear constant slope interval maps? Okay? So we'll do it in parts. So let's start slowly. Okay, so here's one example of something that we definitely want to consider such a map. Okay. So you take a linear Anosov on the torus, such as the Tom map 2111. Okay? So this is a matrix made, multiplication on the left by this matrix produces a map of R2, but because this matrix is an integer matrix, it preserves the Z2 lattice, and because the determinant 1, you can actually take the quotient by the Z2 lattice, and it produces a homeomorphism of the torus. But it's much more than a homeomorphism because the torus has a linear structure. It's just R2 mod Z2. So, Euclidean structure on the torus is Euclidean structure from R2 projects to the torus. So it's still there. You can measure distances. You can draw triangles. You can do geometry if you want on this torus. And this map here was linear up in R2. It remains linear on the torus. Right? I mean, you just squeeze by, and this matrix here, even though it's 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 not diagonal. It can be made diagonal because it's diagonalizable after all, but it's symmetric in particular. And then, in its diagonal form, well, it can be made diagonal by perpendicular, actually, eigenvectors. And in its diagonal form, it squeezes everything by a factor of lambda and stretches, well, squeezes by 1 over lambda and multiplies by 1 over lambda. Okay? So it's this is so that's the sort of the most PLCS map that you can think of, perhaps, in the world. Well, okay, so that's a good first example, and then there's some interesting observation that this map admits an involution by z goes to minus z. You can take the quotient by that involution, and that produces again a map which continues to be linear because this involution here respects the Euclidean structure, except on the torus and R2, except that there are 4 points where some maybe slightly interesting things happen. But anyway, there is a Euclidean structure all over the sphere, which is the quotient of the torus by this involution, except at 4 points where this Euclidean structure gets a bit deformed. Well, it's not deformed actually; it gets quotiented by because there's the fixed point here and a period 3 point there. Well, of the map, but not of this involution. But in any case, at these points, the Euclidean structure gets quotiented by a 180-degree rotation. Okay, so that produces a cone point of angle pi. Okay, but fine. So the map still is the squeeze stretch in an Euclidean structure. Okay, with singularities. All right, so I'll define pseudo-Anosov maps to be exactly maps like this on any surface now. Okay? So what is a pseudo-Anosov map? Well, a pseudo-Anosov map is a surface homeomorphism which which is linear made with diagonal matrix on a surface which has an Euclidean structure. Now, Euclidean structures, strictly speaking, only exist on the torus, because of Gauss-Bonnet or something. But if you allow conic singularities, they exist in every surface, right? And I'm allowing these conic singularities of angle pi, 2 pi. Well, 2 pi is not the singularity, 3 pi, 4 pi, integer multiples of pi. So you allow those things. So now these Euclidean structures exist on every surface, and that a pseudo-Anosov is a map that has such an Euclidean structure, and it acts as a diagonal matrix that stretches one direction and squeezes, the perpendicular direction. That's what it is. Okay? Now, so to talk about Euclidean structures with singularities, so it's important that these singularities have these integer multiples of pi as singularity as conic points, or else you need to know what horizontal and vertical directions are. Okay, so that's why you need these. Okay, so that's what a pseudo-Anosov map is, and these Euclidean structures have finitely many singularities. Okay, to start with, that's what a pseudo-Anosov map is. So you can relax this condition a little bit and allow for infinitely many singularities infinitely many singularities, but only finitely many accumulations of such singularities. Okay? So that's something else that okay, so let me give, okay, so here's an example of a pseudo-Anosov map with 4 singularities of angle pi. And here's an example of something else that we have seen, some form in, study dynamics. Most everybody has seen the horseshoe, and here is a tight version of the horseshoe. Okay, so I'm going to define a map on the square, and then I'm going to fix the map later on because this map's going to have 2 problems. So here's the square, which I'm calling Q, and the square gets squeezed vertically and stretched horizontally. So this blue point goes here, the red point goes there, gets squeezed by half and multiplied by 2 or horizontally, and then you cut it along the dotted line like that, and then you fold and you put it back here so that the blue point gets down here and that red point gets folded here, and then you place it back on top of itself. Okay, so and it fits perfectly, right? Because I've squeezed by 2 and multiplied by 2. However, there are problems, right? I mean, this map is neither continuous nor injective. It's not continuous because I had to rip, right? I have to cut here to open it up, okay? And it's not injective because the top of here and the top of there map to the same line here if I want to put it really back there. I separated here just so we could see, but, I really want to put it back there. So there's, the separation doesn't exist. So I've denoted the ripping singularity, the ripping problem, the discontinuity in blue and the lack of injectivity in red. So it's discontinuous and non-injective. And then we want to fix this. And how we fix it? Well, we fix it by gluing together things which are ripped and gluing together things which map to the same point. Okay? Because that way, so if you glue together this top part to this bottom part, when you map this guy to the left sort of side to the bottom and the right side to the top, well, they're the same now, so you don't have to rip anymore. Okay, so I'll tell you. So I'm constructing this map here. Take a square, squeeze vertically and stretch horizontally by factor 2, cut it along here, and place it back inside of itself. Okay? And then I'm fixing that map, which is neither continuous nor injective, by gluing things together. So I'll glue the top part of the right side to the bottom part, because in that way I don't have to rip it anymore. But once I glue the top to the bottom here, I have to glue its image and its image and its image and all its infinitely many images. And the same thing for the non-injectiveness. If I glue this half to that half, because they both are going to map to the same place, well, then that fixes this non-injectivity, but then I have to fix the pre-image of non-injectivity and all that. And here is what I have to do. Okay? So I have to take that square there, and I have to glue the top here to the bottom there, glue the left to the right over here, and then I have to glue all the images of this. So the image of this, if you look back here, the image of the right side goes to here, goes to there, and then it goes to there. Okay? So I have to, so if I glue this to fold it in half, the top and bottom, I have to fold this in half, and then the image of this is here, the image of this is there, etc. With infinitely many glues, and the same thing, the backward images. Well, this map is completely symmetric, and so this non-injectivity here comes from there, which comes from there, which comes from there. Okay. So and then, okay, so now here is another extremely Euclidean space. Right? Hardly anything more Euclidean than a square. Right? Well, except that you've done some things. So here is a point which is a cone point of angle pi. Well, why? Because there's only pi angle over here, and there's nothing on the other side. You just glue it itself. And here there's another conic point of angle pi, and so on. So you get infinitely many cone points of angle pi accumulating at this bottom point over here. Okay? Well, all right. So you might say, well, this is not very Euclidean. It isn't, right? And it's not even anyway. But it's an accumulation of singularities. You can maybe try and understand it a little bit, but it's sort of an essential singularity. Okay, and then but inside the square, the Euclidean structure is very Euclidean. And what does the map do? Well, the map does what it has to do, right? It divides by 2 and it multiplies by 2. It squeezes vertically by 2 and dividing by 2 and stretches horizontally multiplying by 2. So that's an example of a generalized pseudo-Anosov map. One which lives on a Euclidean surface with singularities, perhaps finitely many accumulations of singularities but on this Euclidean structure, it has this diagonal matrix, lambda 1 over lambda. Okay? So that's the easiest, perhaps, pseudo-Anosov. All right.
André.
Oh, yes.
So not the points that are singularities, but the point in the middle between the two singularities. What is the geometry? Yeah, for instance, what is the geometry in a neighborhood? They're all identified with each other.
Yeah, so this is identified to that, is identified to that, is identified to that. Infinitely many points are identified, and in fact, you have to glue them to this bottom point here, and then the geometry around it, it's a bit complicated. But anyway, so
the infinite that angle there.
Yeah, in fact, yeah. So I had a master's student who actually studied the geometry, and then you can actually define an angle structure around it, but you can't sort of close it up. So the angle, the space of angles there is like an infinite real line.
You have pi for each pi.
Right. No, right, and there's Gauss-Bonnet. So, and Gauss-Bonnet says that the Euler characteristic of the quotient space is the sum of 2 pi minus the cone angle. Right. So, for example, in this example here, there are 4 singularities of angle pi. So 2 pi minus pi is 4 pi. So, oh yeah, right. So it's 2 there's some Gauss-Bonnet that you have to multiply something by 2 maybe. But in any case, there's some Gauss-Bonnet here. With here, you have to add 4 pi. So it's 2. Oh yeah, 2 pi times the Euler characteristic. Anyway, so there's some Gauss-Bonnet, which here works, except that because you are adding. So right. So sorry. Cone angle smaller than pi is positive curvature. Right? And here there's a definite amount of positive curvature around each one of these guys. There's curvature to pi, so to speak. Okay? And Gauss-Bonnet says, I think it has to have 4 pi curvature on the sphere. Right? So you have to have infinite negative curvature around this point here if Gauss-Bonnet is going to work. Okay? But anyway. Okay. All right. So now we've defined these maps, pseudo-Anosov and generalized pseudo-Anosov maps. But remember, they're sort of fun, but we have a purpose here, and the purpose is to try and construct piecewise linear constant slope maps, which are supposed to serve as models for two-dimensional dynamics. Okay, and then you might wonder, well, how many maps of like pseudo-Anosovs or generalized pseudo-Anosovs are there? And here is so let's talk about this. So, for example, pseudo-Anosov maps themselves, well, they happen quite often, and in fact, they were invented or been given this name by Thurston for his classification theorem of isotopy classes of surface homeomorphisms. So Thurston has yet another fantastic theorem that classifies isotopy classes on surfaces. Okay, so if you look at a surface and you look at a self-map of the surface and you allow to move, the map by isotopy, you can ask yourself whether you can classify those isotopy classes. And Thurston did that and said that there are 3 types of isotopy classes: finite order ones, reducible ones, or neither. Okay? So finite order ones are isotopy classes that after finitely many iterates come back to the identity. Okay? Reducible ones are isotopy classes that you should really not be looking at that surface. Right? because that surface can be cut up. You cut it up putting simple closed curves, and then you look at the first return map to each. You cut it up into finitely many pieces, and you look at the first return to each piece. Okay, so that isotopy class sort of doesn't really, it's not fundamentally there. It's somewhere else. Okay, and if it's neither of these two, it's pseudo-Anosov. Now, well, pseudo-Anosov means that there is a pseudo-Anosov map in that isotopy class in particular. Okay, so you might say, well, okay, so but not only that, pseudo-Anosov isotopy classes. Not only do they exist, but they are actually quite abundant in the sense that most isotopy classes are actually pseudo-Anosov. Okay, so pseudo-Anosov maps do exist. There are many of them because of this theorem, perhaps. All right. So how about generalized pseudo-Anosovs? Well, generalized pseudo-Anosovs are quite abundant as well. And in fact, here's one way of constructing them. If you look at some Markov map, Markov graph map, which lives on a surface, and to live on a surface means that if you take a Markov graph map, which can be realized as a near homeomorphism of a surface, okay? And then you also assume something that is preventing the map from being finite order or reducible. You ask it that its transition matrix be irreducible aperiodic. That is, it has a one of these Perron-Frobenius eigenvalues with absolute value greater than 1. So then that graph map, whoa. Oh, I see. The example comes later. So you can construct a generalized pseudo-Anosov out of such examples. It might turn out to be pseudo-Anosov, but okay. So here are the examples. The examples are not in the order in which well, anyway. So here are examples of pseudo-Anosov maps. Okay, so these braids on the plane, they determine isotopy classes, and here are two examples of braids. For which the isotopy class they determine are pseudo-Anosov. So this braid here, in fact, determines exactly the isotopy class of that quotient of the 2, 1, 1, 1 thing to the sphere.
How the braid determines homeomorphism of the surface? Braid and the one. You say they are braids are invited with isotopy classes. So
right. So you think of there being a plane, maybe, or a disk up here, and the same. Yeah, this is a three-dimensional space, but you think of there's a sort of a cross section here, which is a plane, and the plane down here too. And then you make this braid out of wire, and the plane is made out of rubber. Then you push the rubber down, and that determines sort of a map, maybe. But it really, the rubber, you can vary the rubber
because it's a puncture.
It's a puncture. Yes, it's the puncture plane. I'm puncturing at these 3 points, and in fact, I'm puncturing at infinity as well. And then the wire forces you to do something, but that doesn't really matter where the wire is. When you push, no, it's certainly not. Yeah, but by the time you come back to the 3 points, then you've determined some sort of map on the rubber plane, and then that's an isotopy class. Yes.
There are ways to what is lambda?
You speak up, please. I can.
I'm saying what is lambda in this case when there's a braid?
Yeah.
Can you find that?
Yes.
Yeah.
You can. But anyway, there's work to be done here. You have to find something which leads to an invariant train track, which has a transition matrix, and finally you find some polynomial whose biggest root is lambda. Okay, but there's a process, and I'm not saying that this is trivial at all. I mean, there's a whole classification. What?
That's for torus can be looked at as horizontal strip and vertical strip. This matrix 2, 1, 1, 1 is composition of horizontal twist and vertical.
Right.
And you can sometimes build a surface as split horizontal strip with singularities and also vertical. And then your A, eigenvalue is just, it's okay, you have find structure, you have find structure of horizontal is the same on vertical. Here, and matrix A. This is composition of horizontal to me. Okay, maybe it is not general Shibano. It's a special class of Shibano.
No. Or on the torus.
And this is
This is on any surface, but yeah, it's not only on the torus, but.
yes, only. But we
You can take multiple,
but
yeah, you can
use it Shibano.
not all Pseudo-Anosovs are given.
Yeah.
But you can have multi-curves on this surface, right? And you do day twist on, so it's multi-curves, and then we take, and then we take another collection, a transversal collection, you do day twist on the other one. And then most of the time, this composition would be.
Yeah, that's what
But this is more general.
Then you obtain something like translation surface. You have atlas built from vertical strips and horizontal, and you have fine structure.
right, which is this Euclidean structure that I'll talk.
There is a category for this translation surface.
Yeah. So yes, Euclidean with the horizontal direction and a
And
vertical.
vertical direction.
Okay, but anyway, so they're I think what they're talking about are methods for constructing pseudo-Anosovs. But just like so the other side of this is the following. So write yourself, take a braid on 7 strands, and write the braid, any braid. Okay, chances are it's going to be pseudo-Anosov. You just do it, okay, and it's going to be pseudo-Anosov. Now, how do you find out that whether it is or not? That is not easy at all. I mean, you have to work, okay? So you have to find an invariant train track. There are algorithms, people, publish, long, difficult papers about how to find, an algorithm for finding the pseudo-Anosov structure. It's definitely not simple. It's something that requires work. Okay? But what I wanted to say is that these things do exist, and they exist, and there are a lot of them. That's what I wanted to say here. But I'll say, so she's going to do just a second. What I'll say next is that there are many of them, but not enough. Yes.
Are there conditions in the brains to know that they are pseudo-Anosov?
Right. Right. Well, one can try to find. It's very hard to find a condition that is easy to read off. I mean, one thing there's an algorithm, and there are computer programmers that implement this algorithm. And then, if you give me a braid, I can go to the program, I can give it to the program and ask. Right now, a general answer, you can answer this. Well, Michael Handel has a paper in which he solves this problem for 3 braids. And I know that he worked on this on the 4 braid problem, and it becomes powerfully complicated. And I think he never kind of got to the end of that. So, the fact that they exist, it's a fact. I know it, you should believe me, but I've worked on them for many years. But asking, so if I give you a braid, am I going to be able to tell it is pseudo-Anosov? Well, even after working on this for more than 20 years, I would have to think about it and might not be able to answer very quickly. Is that? Yeah.
Is it possible also to relate this to constructing pseudo-Anosov from graph? Like, since there are
right. Let me get to the graph example, and that is a lot cheaper in many ways.
One test is, can you give me some additional braids with permutations, but can you tell me like set of braids? What is it?
What is a braid, you mean?
Yes. So is it like some braids will be equivalent? I think.
Yeah, right. So I mean, well, but definitely you have to define it somehow. Maybe take a look at Joan Berman's book. I mean, there's a definition of some. Anyway, so I don't want to try to remember. But what it is this: you fix some, 5 points, 5 points up and down with separate, and then you pass strings, and the strings either pass above or below. Right? And well, obviously it doesn't matter where these strings are. I mean, provided you don't cross them.
But if you number 5 and then move to the lower, then you obtain locally three-dimensional sphere.
On but he had a great I didn't even know to
Sometimes not.
right. There's a whole vast
Is just equivalent to what is
no,
it's not.
definitely not. No. Okay. Yes. No, definitely not.
So it can be described using genetic relation similar symmetrical group. So you have SI permutations of consecutive numbers. You will not have SI squared equal to identity as in symmetrical, but the rest relations are similar. So you can define it in this way.
So you can, I find it a bit sort of a letdown to describe such beautiful geometric objects in terms of generators and relators, but you can do that. So it's a group so the braid group on n elements has n-1 generators, which are the braids that just turn 2 strings. And the relations are, any 2 commute, provided that they're 2 apart. And if you do this, the next, and the next, then there's a relation there. But so that's a group, a theoretic version for this thing. But anyway. Is that all right? Okay, so here is an example of an easier way of producing not pseudo-Anosov necessarily. This is more often than not, you're going to get a generalized pseudo-Anosov out of this type of example. So you start with any graph on a surface, okay? And then do some map on the graph and the map has to be Markov in the sense that it takes edges over edges. You can't backtrack and do funny things. Well, if it backtracks, it has to be on a vertex. Okay, so it has to be a Markov map. And then it has to live on the surface in the sense that you have to be able to realize this map of the graph. So you put the graph on the surface, and then you realize the map on the graph as a near homeomorphism. That is, as a homeomorphism of the surface, which restricted to the graph, at the very end, it becomes this map here. So for example, this one, I've mapped this triad here like that. So, A maps to A, B, and B, but, I'm leaving them separate here so you can see, right? But what I really mean is that F of A, covers B, and covers B back. Okay? And then F of B covers C, and F of C covers A. Okay, and then this has a transition matrix, A, B, and C. So A goes over A and B twice, 1 and 1 here, and goes 0 times over, and I left the 0 out because I find it easier to not read 0. It doesn't go over C, and then B goes over to C, so B goes over to C here, and C goes over to A, and that's it. And then if you iterate this matrix like twice, I think it's already all positive. So this is a Perron-Frobenius matrix. You compute its leading eigenvalue. It's something. It's lambda. Okay. And okay. So then there's a recipe for how to cook up the generalized criminals out of this, which I could maybe can show you. But in any case, there's a recipe. You just do things. You can each of these edges here gets changed to a rectangle. The side of the rectangle has to have sizes which are given to you by the vertical and horizontal eigenvectors associated to the transition matrix and blah blah blah. Okay, so and then you glue things very much like I've done with the Hosh. Okay, so that's that's a much sort of cheaper sort of way of producing pseudo-Anosovs, except that most of the time these are going to be generalized pseudo-Anosovs because we have to allow infinitely many singularities. Okay. All right, and I made all right. So in the previous lecture, I mentioned an example of an OMAP, which I said was hyperbolic by Zenorized program and all that. And this is the one-dimensional version, the reduction to the graph map, which corresponds to that example. in fact, or I believe it does. I don't didn't prove anything. But in any case, this is and that is the transistor matrix that Juan Valentin Mendoza used to calculate the number of periodic orbits, which matches the Bingham-Wenzel program and all that. Okay, so these are okay. So all right, so now we're getting to the point of counting pseudo-Anosovs and generalized pseudo-Anosovs. Well, there are ways of producing these things. Some are easier, some are harder, but they have a problem if we want to use them as models of piecewise linear constant slope maps in dimension 2, that they form a countable family. Well, up to conjugacy. So they form a countable family. And this is a serious drawback. In fact, it's an uncountable drawback. Because, if you're studying a family of maps parameterized by a parameter, a real parameter, then unless the family is trivial, you expect to have uncountably many different dynamical systems. And so you can't expect to model uncountably many dynamical systems by countably many models. Okay? So that's the drawback that we have to, So if you want to come up with models for all maps in the Milnor or Losey families, for example, the pseudo-Anosovs and generalized pseudo-Anosovs are not going to do the trick. Okay. So what we'll do is to construct to define to define a wider class of maps, right? But before doing it, I wanted to do a cultural interlude. Okay? I'm going to show you pictures of beautiful paintings of some. No, I'm going to talk about math, and I'm going to talk about two theorems of Thurston, one of which I already have talked about. So there are two, sort of mathematicians. Scientists, I suppose, are trained to not, express emotions, but it's hard to be sort of indifferent. So Thurston proved many fantastic theorems, and these two are, part of this incredible work. And one of them is this classification theorem that I already mentioned, that you can classify mapping classes, right, or isotopy classes of surface homeomorphisms. And so a surface homeomorphism is isotopic to one of three types. One which is finite order, reducible or pseudo-Anosov. Finite orders, like I said, after finitely many iterations come back to the identity. Reducible means that you can cut up your surface into a simpler simpler pieces that get permuted, and then you look at the first return map, so you shouldn't really be looking at that mapping class of that surface. And then pseudo-Anosov are these maps that I talked about, and I'll redefine them in a bit. But the point about pseudo-Anosov mapping classes is that they squeeze in one direction and they stretch in another and kind of bend things around. And then dynamically, pseudo-Anosov maps contain the minimum amount of dynamics in the isotopy class. So, and they themselves are extremely complicated. They have positive topological entropy. They have densely many periodic orbits, countably infinitely many periodic orbits. So they're complicated, dynamically complicated maps, and they're the simplest in their isotopy classes. Okay, so there's no way of getting any better than that dynamic. Right. So the surface here has to have finite topological type. Okay? It has, it's a compact surface minus finitely many points and negative order characteristics. So finite orders are defined. All right, and then there's a second theorem, which is closely related to this classification theorem, which is also an extremely powerful theorem and very difficult theorem to prove because it involves an enormous amount of mathematics, which is the following. Now we're going to go one dimension higher. So you take a surface and a mapping class. F off the surface. Okay, so this is a self-homeomorphism of the surface, and then you do something that one often does in topology. You produce the mapping torus. Okay, so you take the product of your space with the 0, 1 and glue it back by the homeomorphism. Okay, so every time you have a self-map of a space, you can do the mapping torus. Okay, so that's what we do here. So if there's a homeomorphism of a surface, that produces a three-dimensional manifold. Okay. Which is called the mapping torus, denoted by M sub F. Okay, so you product quotiented out by the the relation X here goes to f of X there. And the same conditions apply, it's the surface of finite topological type. And then the theorem is that such a mapping torus admits a hyperbolic structure, and a hyperbolic structure means a Riemannian metric with constant sectional curvature equal to -1, if and only if the isotopy class that you start with is pseudo-Anosov. So there was the classification theorem before, which says that there are 3 types of isotopy classes, and this theorem says that, you know, if you have the 2 first ones, finite order or reducible, then this does not admit a hyperbolic structure. And if you are pseudo-Anosov, on the other hand, this does admit a hyperbolic structure. So this is, you know, a very deep theorem, and Thurston had already proved the Haken theorem before that. This was a theorem that it took him longer to actually to finish, and he never published the proof, I don't think. And in any case, so a lot of mathematics went into this, in particular, mostly for the, well, I mean, this gets into the story as well, but already in this theorem here, the way Thurston proved it was by finding a compactification Teichmüller space, which was a very important compactification. There were other compactifications in place which didn't behave, you know, well with respect to the actual mapping class group, and then that sort of Thurston compactification kind of fixed that problem as well. And this classification theorem is very important, in particular for 2-dimensional dynamics, because it allows you to classify periodic orbits. Every time you have a periodic orbit, say, of a map on the plane, you can, you know, map on the plane, Henon map, say, find a periodic orbit for Henon, and then stick your fingers there and say, okay, I can't let go of these fingers, where these points go, and look at the isotopy class and the complement. Well, Thurston classification classifies that. It's either pseudo-Anosov or blah, blah, blah. And then you can start playing, you know, trying to understand how these things relate to each other because of Thurston classification. And in fact, there's even a partial order on these isotopy classes because of the pseudo-Anosov theory. So this is quite sort of useful and being very important for 2D dynamics. Okay, but then we take a break, right? I wasn't told to take a break, but I'm supposed to be a good boy. And yes.
10 minutes.
Yes.
Question. Go back to the slide and just to remind me, because you write here how hyperpolarization of 3 manifolds with fiber over the circle, and then you talk about surfaces. Could you remind me the connection?
Right. So you take a surface. Product with 0, 1, that's already a 3 manifold, right? And then you glue the 2 ends of this by the map. So that produces a 3 manifold. Well,
So the surface is the fiber. So when you say, I think when you're asking whether these manifolds are, you can get them exactly the same.
so you have your, you have a surface, you product it with a circle, and then you glue it to the, and then you know, then this thing fibers over the circle, because you know you glue the 2 ends of the circle down.
It's like the suspension.
This is the suspension. No, it's not like, it's exactly the suspension. But right, dynamicists talk about suspension. You know, topologists talk about mapping torus. The same thing. That's exactly the suspension. Yes. And right, and then this admits a metric with constant negative curvature if and only if the map, the isotopy class is pseudo-Anosov.
May I ask a question?
Yes, sure.
Okay. What do you mean that it has a partial order? Do you mean if there are some periodic point with some pseudo-Anosov map, then it will force the existence of other periodic points by some other pseudo-Anosov maps?
Right, exactly, yeah. And that follows from what I said a bit earlier, that pseudo-Anosov maps have minimal dynamics in their isotopy class. So the forcing or the implication is this: so you take say a periodic orbit. Well, suppose it's pseudo-Anosov. If it's not, then it's not very interesting. But if it is pseudo-Anosov, then you calculate, say you can do it somehow. arithmetically, whatever, you calculate the pseudo-Anosov in its isotopy class. That map has a lot of periodic orbits, and those are the periodic orbits which are smaller than the given one. But it turns out that this is you have to also prove that this thing is anti-symmetric, right? So if alpha bigger than beta and beta bigger than alpha, then they're the same. This is something that Phil Boylan did, and so it is an actual, honest to goodness partial order. Say it again? Well, it's using Nielsen theory that you prove that it's minimal. Yeah. Is that all right?
So,
Yes, thank you.
Yeah.
Thank you.
Yeah. Okay, so right, so I mentioned that generalized pseudo-analysis and pseudo-analysis alone probably won't do the trick, so we want to define a larger class of maps which will be this class of well, which will contain the correct definition perhaps of these models for two-dimensional dynamics. So here's so we're going to start again. Okay, so I'm going to give another definition of pseudo-analysis maps for generalized pseudo-analysis, which I'll then generalize. Okay. So I said that pseudo-analysis are maps on these Euclidean structures, singular Euclidean structures and stuff. I'm going to define this in another way, which actually is the way Thurston introduced them. So you say that a measured foliation. So we start again with the surface of finite topological type, compact surface with finite many punctures, if you will, and then a measured foliation with singularities is a partition of S into injectively immersed one manifold with local charts. Okay, well, anyways, because I'm going to use these words, but anyway, what you want is to have local charts. Okay? So, and here are the local charts. Well, that's a regular chart, a foliated chart, that you take a chart in your surface, and then your foliation is just a bunch of parallel arcs. Okay? Or you can have a singularity like this, which has 3 separatrices, or 4 separatrices, or 5 or 17 or 24. Okay, so you have these separatrices thing. It can also have one separatrix alone. These are called one-pronged singularities, and they, and these are, you only actually allow them to occur at the punctures when they're punctures. But in any case, and then measured means that you can measure lengths of curves which are transverse to the foliation. Okay, now the way of measuring things is that what you want to know is how much of the foliation this thing crosses. And it doesn't matter whether you cross it here or if you move this arc somewhere else, keeping it transverse and keeping the endpoints on the same leads. Okay? So that's what a measured foliation is. And then here's what the original definition of pseudo-Anosov map was. The surface homeomorphism P, which preserve leaves invariant a pair of foliations, of singular foliations, and this pair of singular foliations are the transverse pair of singular foliations, and they are measured. Okay, so it's a transverse pair of transversely measured singular foliations. And what does the pseudo-Anosov map do? Well, it squeezes one and stretches the other. Right? So this is another way of well, perhaps I have to use more words, but of saying that there's an Euclidean structure with a horizontal direction and a vertical direction. Okay, one of which is squeezed and the other one expanded. All right. So in the generalized pseudo-Anosov is the same thing, except that you allow allow infinitely many singularities with finitely many accumulation points. Okay, so here's some sort of caricature of what a pseudo-Anosov map is. So this is a regular point. So here are the two foliations are blue and red, and here's a singular point. And to be transverse at the singular point means that both foliations have the same singularity, a 3-pronged, 4-pronged, 17-pronged singularity, and they act like that. And so So that's what a pseudo-Anosov map is. And, and from this definition, you can get back to the other one. Okay, and then right in the examples that we discussed, the torus and Anosov, those foliations were exactly the foliations by in the plane, the foliations parallel to the eigendirections, the two foliations which are perpendicular actually, and then these project to the torus, which project to the sphere. And in the tight horseshoe, there are just the horizontal and vertical lines. Okay? So those are the two foliations, one of which is squeezed and the other one is stretched. Right. So the other thing to point out, which is a useful thing to keep in mind, is that you are screen sharing, stop share. Not quite what I meant. I meant one-pronged singularities are the analogues in something or other of critical points. But in dimension 2, these one-pronged singularities are sort of what the critical points are. Okay. All right. So now we're going to generalize even more. At some point when we came up with this thing, it was I wondered if I should call them because generalized pseudo-Anosov are GPAs, right? And then I wondered if we should call them G square PA. Generalized pseudo-Anosovs or something like that. But anyway, so I decided to call them measured pseudo-Anosov maps. Measurable, I think. Oh, sorry, I call them measurable pseudo-Anosov maps. In any case, so we are going to so what we want to do is to allow infinitely many singularities, but we want to allow them, we need to allow them to be dense, for example. Now, if you think about what a foliation with densely many singularities is, you start to have, so what is a foliation with densely many singularities? So and the way to get around this is to use an invariant measure. Okay, so what a measurable pseudo-Anosov will be is something we start with the surface and then we're going to partition the surface into leaves and etc. And I'll give the definition in a second. But let me define a few terms. So we need a measure which is Puzna, meaning positive on open sets and non-atomic. We're going to start and S, well, it's again the closed surface with a measure which is Brel and Puzna. Okay, Brel probability measure, which is positive on open sets and non-atomic, right? So we start with such an object, and then we call it, well, and because this is different enough, we came up with a different name also. So a turbulation on S is going to be a partition of a full Mu measure set into these leaves of the foliation. Okay? And leaf of the foliation, or this turbulation, is an injectively immersed copy of R, right? And these leaves are not called leaves anymore, they're called streamlines, okay? To distinguish between this kind of possibly considerably more complicated situation from the more classical world of foliations or even singular foliations. Okay? And a turbulation is measured if the leaves, the streamlines are measured or have measures in them. And every time we say measure in this business, we want the measure to be positive on open sets, non-atomic and Rodon, so to assign finite measure to compact open sets. Okay, so the streamlines are themselves going to have one-dimensional measures. Okay? And we'll define
are not related to neutral measure.
Right, there will be, but at this point, no. Okay, so yeah, no. And then I'll obviously need two turbulations because I want one thing to be squeezed and the other one stretched. And these turbulations have to be transverse, and transverse means that they meet in a full mu measure set. So the nus are the measures, the 1D measures on the streamlines. Okay, mu is this Puzna measure on the surface, the two-dimensional measure that lives on the surface. And then these two transverse, so these two turbulations are transverse if they meet topologically transverse at the full mu measure set. And transversality is just a matter of two arcs that meet at exactly one point and separate the two components below. So there's such a thing as topologically transverse. And then here's a definition of what a measurable pseudo-Anosov map is. So it's a surface with a Poisson probability measure on S, and two turbulations, measured turbulations, really, which we call tau u, nu u, and tau s, nu s, because one of them is going to be unstable, the other one is going to be stable, or one is going to be contracted, the other one expanded, and we want this expanding, contracting, expansion contracting factor lambda here. And then we want the streamlines to be dense. I'll explain why that in a second, but more perhaps fundamental is that I want these. So now I have two turbulations which are transverse, and then each one of those has a one-dimensional measure, and I want these two one-dimensional measures, when you do the product of them, to produce the original measure.
But maybe you need the assumption that both populations are measurable.
Sure. I should have said that.
Measurable partition.
Yeah, well, I think I said it here. Yeah, we're going to do that, but so,
It's the Y.
yeah, sure. But I'm saying these are measurable sets, right? I mean, and they have no measure.
Not about measuring.
I know. Yeah. Anyways.
The partition is measured.
Yeah.
The uncountable
Yes.
partition is measurable if it's not.
Right. Right. Yes, but anyway, this is right. So what exactly this means is pretty tricky. Okay, so you have to define this very carefully, and we have had a lot of grief trying to pin down exactly what we mean by that.
No, but you can say that you can.
But there's no
System
quotient.
of conditional measures,
But
the measurable partition. Then there are systems of conditional measures. And these fibers, US and U, and the integration of one system with U and another system is also.
The problem is that the streamlines are dense, so there's no obvious quotient or projection.
Oh. Measurability. Okay, go on.
Anyway, right. So we thought a lot about this, and we ended up kind of circumventing this problem of, which seemed to be a problem. Maybe it isn't a problem, but talking about something else. But in any case, so there's an issue here that has to be dealt with. And then again, one of the turbulations is squeezed and the other one is stretched. Okay, so that's the. And then, right. So let me say a few words. Well, the original measure sees the whole surface, and then the turbulations occupy all of it. Or the turbulations, are dense, or at least dense. They occupy full measure, but in particular, since the measure is positive in open sets, they're dense. So the condition about squeezing and stretching is the usual hyperbolicity condition, that one direction is contracted, the other one is expanded. And right, the expansion and contraction factor are lambda. Okay, they're the same. So this is the constant slope, or the constant hyperbolicity in story number in this business that's lambda. And this product condition here is quite technical. So we did think about measurable partitions and things like those. But anyway, we ended up kind of defining this slightly differently by talking about something else, because we have to worry about a handful of things. In any case, yeah. But anyway, but there is some sort of technical words that you have to say to explain exactly what this means. But in the usual pseudo-Anosov case, or a generalized pseudo-Anosov case, what this means is that the same thing as saying that two-dimensional Lebesgue is one-dimensional Lebesgue times one-dimensional Lebesgue. That's sort of the generalization for this more complicated context of this sort of basic fact. And then condition A that we want streamlines to be dense is to avoid reducibility. Because we might, so if we have a generalized, measurable pseudo-Anosov like that, which lives, sort of has two independent pieces, we sort of want to separate them. Okay, so that's why we require that that they be that the streamlines be dense. Okay, all right. So then there's a theorem. So the theorem or a theorem, which Phil Boylan and Toby Hall and I proved, which says the following. So you might ask yourself, I mean, this definition is complicated enough. Maybe it's great, but it doesn't, it has the empty set for its realization. Well, so here's a theorem that says that no, there are many pseudo-Anosov, measurable pseudo-Anosovs, and in fact, they do the trick, at least for this context here. Okay, so here's the statements of the following. There exists a one-parameter family of measurable pseudo-Anosovs. Okay? So one parameter meaning a one real parameter that, and the parameter is this parameter S here that varies between square root 2 and 2. And these measurable pseudo-Anosovs actually imitate or mimic the dynamics of the 10th family. Okay, so the 10th family, or that family that you know, that model was the geometric models for unimodal families in general, but in particular for the quadratic family. And for the parameter varying between square root 2 and 2, we really said that the parameter should be S should be bigger than 1. But you know, in this case here, we want the map to be non-renormalizable. That's why we want it to be bigger than square root 2, really, is a bit farther up. But in any case, there's a whole, you know, an entire interval. You can see the 2 behind Žemek 2 is behind him, but anyways, 2 there, square root 2 and 2. Okay, so more precisely what this family of pseudo-Anosov and measurable pseudo-Anosov does is the following. So for each S, there's a semi-conjugacy from the inverse limit of the 10th family to the sphere and with this measurable pseudo-Anosov. Okay, so for each parameter S in this range here, you take the 10th map, take the inverse limit, which is drawn here, so caricature here. So here's the 10th map for parameter S, you take the inverse limit, and then there's a semi-conjugacy to the sphere, and on the sphere, there's this measurable pseudo-Anosov here. And this, and the fibers of the semi-conjugacy have at most 3 points. So most points have exactly 2 preimages. Some finite countable collection of points have 3 preimages, and there's one special point that may have more points in the preimage set. Okay, and this preimage set may actually be infinite, uncountable even, but it does not carry any entropy. Okay. So anyway, I can say exactly what that means, but in any case, so this semi-conjugacy is quite mild in the sense that it does not really alter much the dynamics here. It only kind of places it carefully on the sphere. All right, so and then, okay, so then here is a family, right? So of measurable pseudo-Anosov that really vary continuously with, and they do vary continuously. Actually, this is something else that we proved, that they vary continuously with this parameter S, and form, you know, therefore an uncountable family of measurable pseudo-Anosov. Okay. Okay, so some words about this theorem is that, you know, there's a dense subset of parameters for which the critical orbit is finite, right? So we post-critically finite. Okay? So there's dense set of slopes for which the 10th map has this post-critically finite orbit. And every time you play, you know, this game here with a post-critically finite turning point, then this construction produces not a measurable pseudo-Anosov in all its complicated glory, but a generalized pseudo-Anosov, that is one which has countably many singularities with finitely many accumulation points.
Sorry, but this set is countable or uncountable?
This set is countable. Oh, yeah, sorry, countable dense. Yes, sorry. Yeah, countable dense. There's a countable dense. Okay, sorry, I forgot to write here. Countable dense set of parameters for which this is supposed to be finite, and for those, the measurable pseudo-Anosov really is a generalized pseudo-Anosov. So there's in fact a subset, a countable, very much non-dense subset of this subset, for which the generalized pseudo-Anosov is even simpler, is an actual pseudo-Anosov map on the node with only finitely many singularities. Okay. And this set is also countable infinite, but it's very much, it's very sparse, so to speak. And that was described in Toby's thesis many years ago. All right, but this accounts for, countable many parameters, and all the other parameters have genuine measurable pseudo-Anosovs associated with them. And in particular, there are many pseudo-Anosovs here which will have really densely many. So every time the critical orbit of the 10th map is dense on the interval, then the singularities of this thing are going to be dense on this turbulation upstate. Yeah. Right, and then the final remark here is that the exceptional fiber of the semi-conjugacy has typically three or more finitely many points, but anyway. And then there are some cases which are few and far between as well, in which there's a Cantor set. But those cases are very well understood, and those Cantor sets are rotational Cantor sets. So the entropy is zero there too. So it's this is very well sort of understood, everything that happens. Yeah?
Excuse me.
Yes.
Does this set of parameters for which you have pseudo-Anosov maps has anything to do with hyperbolic logistic maps?
Anything to do with what? Sorry.
To do with hyperbolic logistic map. The 10th map are somehow unimodal maps, and we have infinitely many unimodal maps for which we have a unique attracting cycles. And these are infinite but are not very dense, let's say, something like this. Does these parameters has anything to do with those parameters in logistic family?
No, sorry. I think it's better to forget the logistic family here. They don't have anything to do with. They're very specific parameters where the critical orbit is periodic, but it is the periodic parameters for which this occurs are very, very special. They have to satisfy some quite special conditions on the type of permutation of the periodic orbit for the map Phi to be pseudo-Anosov on the nodes. But it doesn't have anything to do with attracting. Yeah, forget quadratic family now, but and the 10th family there are no attracting fixed points. And those play no role here actually.
Okay, thank you.
Is that all right?
Yes, thank you.
Okay, and okay. All right. So I wanted to show a picture of these laminations, what these laminations look like, and here's a lamination. Well, so that's a lamination, and that's sort of what you should kind of think of. When you think about one of these measurable pseudo-Anosovs, except that this is not measurable pseudo-Anosov, this is an actual generalized pseudo-Anosov. And let me tell you, so there's some. Well, in fact, the lamination really is only the horizontal, the straight horizontal lines here. The bending things, the semicircles, really should be thought of as identifications. That's what those are. So there are these identifications on this, over here, and then the image here is there, is all the way from top to bottom here, and the image of here is down here, and the image from down here is down there, getting smaller, dividing by lambda actually, and then the image from down here is up there, and the image from up there is in the middle here. And the image from here is there, and the image from there is there. And right. So now we're back. Okay, so this guy here is lined up with the big guy. Okay, so this actually is a periodic needing sequence, and in fact, the needing sequence is right here. It's 1 0 0 1 1 1 0 1. So I would see. Okay. But you can imagine that, if you perturb this a little bit and you keep drawing it and you ask your computer to do it, these things are going to be, so this bend here goes to there, that bend here goes to where does it go? Oh, here, and from here it goes to there somewhere, and blah, blah, blah. And these things might be becoming dense in this thing, which they do. Right? So that is an example. Right, so let me see here. All right, so like I think I've been saying all along, these measurable pseudo-Anosov maps, they have, you know, what we think are the good characteristics to make them, you know, deserve being considered the correct 2D analogs of piecewise linear constant slope 1D endomorphism. Okay? And this family in particular is the two-dimensional analog, or, you know, maybe you would like to see it as the correct two-dimensional analog of the 10th family. All right, so I'd like to finish, and I'll finish a bit early, right? Or, yeah. Okay, so I'll finish a bit early, but not quite. Technically, I'll still have 10 minutes. Yeah, no, but I'll finish much before that, and then makes people happy in general. So let me mention some things that I find interesting things to pursue. That, you know, the original definition, well, one-dimensional maps are really linear. Okay? They're linear, you know, and they have constant slope. It's nothing to talk about there. And then I'm sort of arguing that, you know, when we go to dimension 2, we have to, in order to interpret correctly in dimension 2 the fact that a map is linear, really has to do with changing the underlying geometric structure on the surfaces, right? So I argue that, you know, okay, on the tors, all right, there's, you know, you can have actual linear maps, but not on any other surface. All right, but then you allow yourself these finitely many cone points, and, you know, and there's a whole, you know, story around these things, you know, it goes to Thurston theory, blah, 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 Teichmüller theory, you know, quadratic differentials. There's a bunch of things that are, you know, there's a whole world or several sort of connecting worlds that deal with these issues. So, okay, so these are useful, they're present in mathematics, so let's take them on board. And so we have to change the underlying geometry and to talk about these things. Well, but then, okay, so then I've gone quite far here, and I've changed this underlying structure to allow the underlying geometry to be completely sort of, you know, lost, so to speak, because, you know, okay, putting finitely many cone points is all right, putting infinitely many with accumulation points is already something that, you know, so what is the geometry around these accumulations? Well, that's a bit tricky, and I mean, let alone if you let this become dense, right? Okay, and then, you know, then talking about geometry, maybe all bets are off, and there's, you know, everything Euclidean sort of is lost. Okay, well, but I don't think it is really, because, you know, maybe metric measured geometry sort of comes, you know, into the story, and it'll allow us to talk about some sort of a measurable Euclidean sort of structure, and there's a sort of so the idea here is to use this measurable pseudo-Anosov, these two turbulations and all that, to introduce a metric, not just a measure. The measure is already there, but also introduce a metric on the surface. And this metric on the surface maybe has interesting properties. For example, it might have almost everywhere defined tangent cones, which is something that metric geometry, you know, you can define. And if you, I mean, not only that, you have almost everywhere defined tangent cones, but also that these cones are not cones, they're actual planes. And then you have an almost everywhere tangent structure to the surface. So this becomes an almost everywhere for maybe differentiable structure. And but the really the way to talk about it perhaps is that these tangent cones, these almost everywhere tangent cones, define or allow you to define a Riemann surface structure on your surface, with respect to which your turbulations become horizontal and vertical trajectories of a quadratic differential, except that the quadratic differential is nowhere holomorphic now, but okay, you can still do that. And then if that, you know, if all that goes through, then, you know, the measurable pseudo-Anosov map is going to be a Teichmüller mapping with respect to this measurable, this integral quadratic differential. And that is, that sort of the idea of what a linear map is. It's a sort of a more perhaps mature way of talking about linear maps is to call them Teichmüller mappings, okay, in dimension 2. But all this is a dream at this point. And okay, that's it. What I had to say today. So thank you.
Other questions from the audience?
May I ask a question?
Oh, I don't the boss.
One moment, Felix started.
Okay.
This way.
So just a second, Felix started. Oh, yeah.
Okay, so I'm sorry because I cannot see the audience.
Yeah, I know. Yeah, just a second.
Go on. Sorry.
So maybe it's not, maybe it is possible like this. Because if you assume positive entropy, then there is a theory for the diffeomorphisms of surfaces with infinite coding, omrisaring and other things. And then you have the Markov partition, anything. And then Markov partition, you have these conditional measures almost everywhere, stable, etc. Infinite symbols maybe do something. But I never think about this, but this is this fantastic theory. It started by Omrisari.
Right. So in fact,
surfaces.
yeah. So that that's what I'm gonna. So because there are the topological sort of theory, and then the geometric side of the theory was two sort of, there was two parts to it.
Yeah, but when you have Gibbs,
right,
when you can use the symbols Markov, Gibbs measures, and you can candidates for conditional stable.
Exactly.
There is all this theory somehow.
So today we constructed what I'm sort of claiming are the correct analogs, and then next time around I'll talk about how do we do the semi-conjugacy and what we expect to hold, which is also sort of not completely proved, but in any case, what we expect to hold, how to start with the diffeomorphism of the surface and go down to one of the models, semi-conjugate to one of the models, and then this theory sort of would get into the story. Okay, so can I? So, yes. What is? So I don't know who. Okay. Yeah, go ahead.
Okay, may I ask now? Okay.
Yeah, sure.
I have two questions. The first one is that are conservative and dissipative dynamics taken to be the same for having models, or there should be some difference for modeling these two kind of dynamics? For example, if we want to model conservative Henon maps, we should use some other models, and if we want to model dissipative ones, the other models. Because in conservative, we may have elliptic periodic points and some new phenomena may happen.
Yeah, right. So right. I mean, next time around, I'll talk about a semi-conjugacy, right? Now, the semi-conjugacy, well, it works irrespective of conservativeness but I this whole theory has typically in mind dissipative maps. Okay, so it may also work for the conservative case, but then the semi-conjugacy might kill, a lot of very interesting stuff, KAM theory, this, that, and the other. And I don't, it might be killing stuff that you sort of may not want to kill. But in any case, on the one hand, what I've talked about today, or what we're going to talk about next time, doesn't see them tomorrow, right? And it doesn't matter. On the other hand, it may be, it may not be very efficient and very, very useful to consider to do this kind of quotient in the conservative case, and you might want to be more, more conservative in that case and kill less stuff.
I see. Okay, thank you. And my next question is more explicit about the partial order that you noticed. I want to ask a question to understand more about this partial order. Suppose you have a map on a surface, for example, plane, and it has two different cycles. That restriction of f when you omit each of cycles, the f restricted to the rest of the surface is pseudo-Anosov. And these two orbits are not comparable with respect to that partial order.
Yeah.
What happens if you omit both of the cycles? First, is the f restriction restricted to the rest of the surface still pseudo-Anosov? And if yes, is it the smallest smallest element in this partial orbit, which is biggest than these two pseudo-Anosov maps or not?
Yeah, I haven't thought about this for a long time. It probably is, but yeah, probably is, but don't have to think about it. I haven't thought about this for quite a while. So the question is, if you take two orbits, both of which are pseudo-Anosov, but neither implies the other. Now take the two together, and that will be pseudo-Anosov, I think. Anyway, even that you have to think about. But anyway, and then, well, if it is pseudo-Anosov, now compute the pseudo-Anosov. Is this? Well, I think. Well, anyway, probably is sort of by definition, right? Or by Nielsen theory. I'd have to think about this.
Okay.
Anyway, so sorry, but I can try and maybe talk. Yeah, sorry.
Actually, I'm asking this because you told the pseudo-Anosov maps are countable, so they cannot, they have not the strengths to characterize dynamics in which have in parameter families which have uncountably many dynamical types. And I was thinking, yes, these may be countable, but the sequence of pseudo-Anosov map, we have in uncountably many sequence of pseudo-Anosov map.
Right. You could ask. Yes, this is a question that I could have put here somewhere. Is it true that you can take the closure in some reasonable sense of the collection of all pseudo-Anosovs on a given surface? So to take the closure in the C0 topology, we have to worry about some things, but in any case, you do it. So is that closure, does it coincide with the set of all measurable pseudo-Anosovs? That's a very good question. I don't know how to answer that. But yes, that's another way. So, which would be like to say, okay, so you never consider any map with infinite needing sequence. You only consider maps with finite needing sequence. And then every time you want to talk about an infinite needing sequence, you don't talk about it. You talk about the sequence of needing sequences that becomes more and more infinite, but they're all finite. But yes, it's a very good question. I don't know the answer.
Okay, thank you very much.
Yeah. Okay. Yes.
You said we should not talk about it, but which needing sequences give rise to the honest pseudo-Anosov maps? This is Toby.
This is Toby's thesis. Yeah, he gave them this funny name. What?
You remember which ones are like?
Oh, I remember very well. Yeah, I don't know. Yeah, but anyways, this is a long list. There's an infinite list. There's a countable list.
So, one example of something like
that. One example. This is an example. The other one wasn't, right? Okay, let me be less coy about it. All right, so look at this picture here. So every finite needing sequence, well, every needing sequence produces a picture like this, but in particular finite ones. Okay? And then every time you draw this drawing here, what is that? That is this. You take the tenth map or the unimodal any map, and you go like this. So you think of the unimodal map as taking an interval and stretching it and bending. Okay? So you do it here, and you bend it, and then you bend it again, and you bend it again, and do it, a lot of times, and then what you see is this. Okay. And then if you start doing it in varying parameters, you start to see the following thing. So this is the critical value. This is the second image of the turning point, third, fourth, fifth, and then and then you draw these pictures and you vary the parameters, and then sometimes actually pretty much always so if you take finite leading sequences, the picture is always like this. It goes around a few times, and then eventually it gets to the top here and goes inside this. There's a big sort of tube here. Okay? It goes inside here. And this always happens for finite leading sequences. Always. But one thing that can happen is that this guy, when it goes inside for the first time, it goes inside exactly at the critical value. That is, the topmost guy here exactly lines up with the critical point, or the critical, direction here, the critical level here. And those are exactly the ones which produce pseudo-Anosov maps. Now, for that to happen, there's some very specific combinatorial, properties that the needing sequence has to have. And it's possible to list them. And in fact, what happens is that there's a circle at infinity here, and the circle prime, the circle prime ends that looking from infinity, the map on the circle prime ends is a rotation, and it's for most parameters it's a finite rotation. And then you see these plateaus. For every rational rotation between 0.5, you see these plateau of needing sequences for which they all have given finite rotation at infinity. And in the middle of each one, in the middle, somewhere inside each one of these plateaus, this miracle happens, and the miracle is that this guy, whoops. So, this thing here, as you move with a fixed turning at infinity, this thing moves from left to right, or right to left, or whatever. And there's exactly one instant in which it maps exactly to the turning point, and that's the critical. That's the pseudo-Anosov case. And then you can, there's a theory for the needing sequence which this happened. You can explain this. Yes.
So, is there any connection between the rotation number of the prime ends and the measured pseudo-Anosov?
No. So for the rotation of the prime ends, well, there is some connection. It's not very strong. But for every rational rotation number, there's a whole interval of needing sequences that have that rotation number, and that interval of needing sequences, densely countably many are generalized pseudo-Anosovs, and the rest are measurable pseudo-Anosovs. But anyway. And these are for the rational rotations, but the irrational rotations are always generalized pseudo-Anosovs. They're never measurable pseudo-Anosovs. I mean,
which ones again?
There are these plateaus, right? These rational plateaus, like Arnold tongues or whatever. There are these rational plateaus, but then there are the irrationals. Yeah. And the irrationals are never, are always generalized pseudo-Anosovs with a singularity, actually.
But no measured pseudo-Anosovs.
Yeah, they're simpler instead of being more complicated. In fact.
And these irrational, are they ever like eventual measurable or
they are? The rotation is always don't draw a type. But anyway, what happens in the pseudo-Anosov? Well, in this picture here. Well, anyway, I'm not sure we'll talk. What is Danjois about it? But anyway, yes, there's some Danjoisness.
No, I mean whether the homeomorphism of the circle of prime ends is of Danjois type, or is it just an irrational rotation when it's irrational? That's what I'm asking. For your final
question. I think it's probably Danjois, but I have to think. I don't know. But it's one or the other. I don't know. I don't know. I have to think.
One question about generalized pseudo-Anosov, where we have it in many functions, but with many accumulation points. So actually, maybe do you know somebody who you worked on it? So how what actually is there any classification of the structure with this accumulation points? Because the Robert said was associated Teichmüller space to depend very much on how exactly the point accumulated. Is it understood? How did
Not, so we construct these examples I talked about here. I know quite very well what kind of accumulation points happen. What we don't have is a very general theory to talk about them. Yeah, I don't. We have proved things like, in the complex structure that these things induce, these accumulation points are punctures. They are not, you can prove that, that they're punctures, that they are not holes. So there's, we can prove some things about them, but there's not a very general theory, And these are infinite dimensional Teichmüller spaces anyway, right? So there's already that. Yeah, but there's no general theory. It would be nice to try and think about that.
Any other questions? Okay, then let's thank you.
Thank you.